Thank you. As Tim said, I'm Kleveter, and today I'll be talking about how to build resilient microservices using the Vapor framework primarily. A couple notes about this talk. I will have various resources that I'll link to throughout the talk. At the end, I will have a couple slides during the Q&A section, so if you want to take pictures of those or write them down, you'll be able to do that then if you don't get them earlier. Also, a lot of what I'll be discussing is more generic, so it doesn't apply to Vapor itself. If you are using a different framework or potentially even using a different language, a lot of the things I will be discussing will apply, and the things that are specific to Vapor will come further to the end, so just to keep those separated so they don't get mixed up with you. Introduction to myself. As Tim said, I'm a software developer that contracts with Skelpo, primarily writing backends using the Vapor framework using microservice architecture, though I have dabbled in some other technologies with that. A lot of what I've written for Skelpo has been open sourced on their GitHub pages under the Skelpo and Swift Commerce organizations, so you can check those out if you'd like to see some of the microservices that I've built, along with some other packages such as one that handles arbitrary JSON structures in a type-safe manner, or a streaming CSV parser. I've been doing Vapor for about 3 years at this point, since the version 1 days, and it's been a wild ride. The core team has done an amazing job building a framework that does an amazing job to build microservices and back-end applications, so big thanks to Tanner and Johannes and Logan for building that. I also hold a maintainer status on several core repositories for the Vapor framework, and those include Async Kit, Codable Kit, and Console Kit. So along with contributing my own patches and features to those, I also help out with pull requests and issues that get submitted to those and then tag releases. You can find me on both GitHub and Twitter. And just as a fun fact about me, I like to eat everything on my plate. So the first time I tried sushi, I saw this green gob, and I sucked the whole thing in my mouth. That was a bad idea. Don't eat all the wasabi at once. All right, so to get into the talk. First off, why do we want to use microservices versus, say, monolithic architecture? And it really boils down to two things: modularity and reusability. It separates our application out into small pieces, and it allows us to take those components and use them elsewhere. So let's say I have my app that handles users. So when I create a second app that also has users, I can use the same component over again instead of having to rewrite the whole thing altogether. And because they are decoupled into separate services, there is less dependency on unrelated features within an application. So some benefits of the modularity in microservice architecture. You can deploy them independently, so if you have different versions of a framework or a completely different language, I know that there are several projects in the community that use, say, Go, for example, because it matched their use case better. You can deploy that to the platform that works best for whatever you happen to be using. Components are replaceable, so if you have a third party that's handling information for you and then you decide to build your own implementation so you can do that yourself, you can easily swap out the component instead of having to rewrite your application to handle that. And also containment of failure. If you write your microservices correctly, what can happen is if you have a single microservice fail, it won't take down your entire app. So even if, say, your payment and ordering fails in your e-commerce platform, people can still browse your product page. And some maintenance benefits of microservices. It gives you isolation of bugs. So once again, if you build your microservices correctly, it can help keep bugs that occur within your code contained versus spreading out across your entire application. As developers, it makes it easier to understand how the code structure works when you're debugging or adding new features that can help keep things contained, and so we can keep track of things better when we're digging through the code base. It increases our rate of evolution, so if a new version of the framework comes out, we can try that out on one specific part of our application, one microservice, versus having to rewrite the thing all over again to test it out to see how we like it. So those are microservices in general, but what do I mean by a resilient microservice? We want to write code that is easy to read when we come back to it 6 months later instead of doing the quick fixes that all our project managers like. So if we bring in a new developer, they can also understand how the project works. Along with being easy to read and write, the code should be something that we can easily add new features to, fix bugs in, remove pieces that we no longer need. So it should be broken down into smaller components and abstracted. And as far as the API and endpoints of our microservices go, we want something that is predictable and that our clients expect and can last a long time instead of having to constantly change how our API works. So an example of microservices that display these concepts, I worked on a project for Scalpo called Swift Commerce, and it was an e-commerce platform that used Vapor microservices for the various components in the backend. So in this example here, at the top we have our front end, and then it connects to the various microservices that I created for users, addresses, an order service, and products. Ralph talked about this yesterday in his microservice workshop, if you happen to be there. So the users will interface with a third-party service for handling emails, and then the Swift Commerce front end will get the user information and can pass it off to any other microservice it wants to. For example, order history. The orders service doesn't actually connect to the users itself if we want to get the history for a single user. Instead, we just have the user ID in the order service, and then the user service itself can be replaced with anything we want if we want to do that in the future. The problem is that a lot of people write microservice architecture that looks like this stack of Jenga blocks. It is fragile. If you try to add something to it or pull a piece out or replace something, the whole thing comes crashing down and you have to rewrite it from the ground up. So how can we write microservices that will hold together and that we can easily replace components with? And that brings us to abstract libraries. Now, these aren't microservices themselves, but while I was working on the talk, I realized that there's a lot of similarities between a library that is abstract that you can easily replace with another library or the implementation with, and how microservices that are resilient are written. So what are some benefits of abstract libraries? They're maintainable. Since they focus on a single concern, you know exactly what it's supposed to do. And so if there's a bug, you can easily track that down in your library instead of having to dig through several layers of operations to figure out where the bug actually occurred. They're pluggable, and since it does handle a single concern, you can take a bunch of libraries and throw them together and you get your application, and then you can take the same library and use it somewhere else for the exact same thing. And since it handles a single concern, you know exactly what your library should do, and so you can easily test to make sure that it works as expected instead of a middle layer somehow breaking and your library actually doesn't have a bug in it. So an example of what an abstract library might look like in the real world. I built a library for Scalpo that handles file I/O, and at the core of it is simply a protocol that handles the CRUD operations for interacting with a file: create, read, update, and delete. And what this allows us to do is create a library for any backend that we want that has the same implementation, so we can swap them out as we like. It comes with a default implementation called local storage that interfaces with the local file system. But I also created 2 other implementations for Amazon S3 and Google Cloud Storage. And then if you wanted to, you could create your own implementation for something like Backblaze B2, for example. And it also has a couple other types in there, such as file, because depending on the whole entire Vapor framework, to get a file type was a little overkill, so I created my own type instead. And so following these ideas of how to build an abstract library, a resilient microservice can take us from a stack of Jenga bricks that looks like this to maybe a Lego tower that looks like this instead, that holds together by itself, that you can easily pull apart and put back together and replace components on. So to recap what we've talked about so far, a microservice architecture can increase your reliability by containing failure and save user frustration in using the same, because if you have a single component fail, the rest won't go crashing down with it. They can provide a better development experience because you can evolve the different services at different rates and it helps you to keep track of the different components when you're adding new features and fixing bugs. So while that can be a good thing, you need to do it correctly. Otherwise, you get what I call a multi-repo microservice, or the better term that I was introduced to was intergalactic spaghetti. So how do we actually build resilient microservices? And it has two aspects, the code on the inside and the API that the client interacts with. So first, we're going to talk about the interface, the API and routes of our microservices. Start out by using a standardized API format. You're going to pick a single architecture that you're going to stick with across your entire ecosystem, and then you're going to stick with that. It appears to me, at least when I'm working around the web, that a lot of people like to roll out their own implementations of REST that mashes in some GraphQL stuff, and then they make a mess of everything, and you have to read the documentation whenever you want to use a route. And that's just messy for both the developers and the client. Nobody wants to use that. So some examples of different architectures you can use include REST, GraphQL, gRPC. Don't use SOAP, it's so outdated. And so what this can do is make your API more predictable in two fashions. When your client is interacting with your API, they know exactly what a route should look like. If they want to, say, create a new model, in REST, they know it has to be a POST request and that they should go with the models collection, and then they can send that request off and it works. And then as developers, we know that if we create a new model and we want routes for that, then we know exactly what the route should look like, instead of having to figure out every single time what the new ones are supposed to be. An added benefit of this is because all of the routes end up looking very similar, you can create a generic controller and then throw any model at it that you want, and it just works automatically. You might want to fine-tune some things that are type-specific, but other than that, you can create a single implementation and save a lot of code duplication. Some resources on this can include these websites for the various architectures, so REST API tutorial, GraphQL, gRPC, check those all out. And since we're using a single architecture to keep things predictable, we can add another layer of predictability and safety using semantic versioning. In REST, your endpoint might look something like this. You have your top-level domain, and then you have your API version, and then after that, the rest of the route. And what this allows us to do is the client can make sure that whatever route they're interfacing with, it won't suddenly break on them when you deploy a new version. Everything will always be backwards compatible. As I said, it adds another layer of predictability and safety to prevent things from breaking on you or another team member who comes along and says, wait, you just got rid of a route I was using. So. And check out semver.org for more information on how semantic versioning works. If you don't happen to already use that, I want to look it up. And since we're doing semantic versioning, you should keep a changelog as a single source that everybody can look at so they know how the library is evolving and what changed since the last version, especially if it's a breaking change. Everybody's going to want to know what routes they can't use anymore, what data points don't exist, to make sure that their app can continue interfacing with your API. Because if you're making breaking changes, what good is knowing that there's a breaking change if you don't actually know what broke? So check out keepachangelog.com to see how your changelog should be formatted so you can keep things consistent, so you can easily search them if you need to, that sort of thing. And another thing that you should do is keep matching data structures across your entire ecosystem. If you have a single data set, you should represent that the same way across all microservices. An example of how this wasn't done, once upon a time I was writing a Swift client for a money transferring API. And of course, they had to represent money. So they had their currency code and the amount of that given currency. And depending on which route I got it from, I had to use either currency or currency code key to get the value from the JSON. And while that kind of worked, you can like dynamically figure out which keys you're going to use when you decode it, but then you try to encode it and you don't know which route you're sending it to, and everything becomes a mess. So keep things consistent for your clients. Also, when a request comes in, there are headers that define what your response should look like, along with the ones that define the request itself. And so the client will send these in to tell you what the response should look like. The examples of what these headers could look like include accept, variations of accept, and the if statement headers. These define things such as what encoding should the data be? Is it UTF-8, something else? Should the response be gzipped? Should it be JSON or XML? If you have a good framework, it can actually handle a lot of this for you automatically. So check out the MDN docs. I know this is a long link, so you could probably just Google it or Bing it or Duck it, whatever you happen to use. So a recap on external resilience and what our API should look like for microservices. Use a standardized API format that people know about and use that across your entire ecosystem on all your microservices. Follow semantic versioning to prevent prevent breaking in changes that when people expect their routes to continue working. Keep a change log so people know how your microservices are evolving and how the routes change. Use consistent data structures so that people know how to decode the data that they get back. And make use of the request headers that are coming in so the client can get the data back that they expect. So that covers what your API should look like, how the endpoints should be structured. But now we're going to talk about the code side of microservices and how you can make the internals better for yourself as a developer. Because what happens is 6 months down the road, you have to change the backend for something, your database, and then you wish you had created an abstraction to swap that out more easily. So what you can do is just read clean architecture, and that basically covers everything. Thanks for coming to my TED Talk. OK, no. So as an example of how this might happen, let's say you're a web agency, and you've created a microservice that several clients use. And it's built on MySQL, and it works great. And then you have a client come along that would be a great client to have. And they say, well, we'll use your microservice, but we have to use this new thing called MongoDB. And not only do you have to tell them that MongoDB has been around for a while, but now you have to create a whole new microservice just to handle a new database. Well, we don't want to do that. So what we can do is we can create internal abstractions for external data, whether that's from a database or a third-party API or even data in files. And so you can swap out where your data is coming from very easily, whether that's for testing or in your production app, if you want to use, say, a different database in this example. And what you can use for this is interfaces, or as in the Vapor community, we call it the repository pattern. What you do is instead of creating two different microservices that interact with different data backends, you add a thin layer of abstraction between the data itself and the microservice, so that what you can do is replace the implementation of that interface itself, and then the microservice just continues to work. So for example, and this is pulled from the address microservice that I referenced earlier in the Swift Commerce site application. This is a repository or interface for the addresses model. I can create an address. I can find them by their ID. I can update it by a given ID with any given data, or I can delete it. And since this protocol doesn't have any self or associated type requirements, what I can do is when I create my controller, I can just have the repository type in there, and then I can instantiate the controller with it, whatever implementation I want. And then the controller just works with it. I don't have to change the code inside of itself. So some things that are specific to Vapor itself. Vapor has a lot of great APIs and abstractions that we can use within our microservices and apps to make things more abstract and easily replace components inside of our applications. So when you have what we have is services that you register with your application, and then you can access those throughout your app, whether that's in controller routes or in a cron job or somewhere else. And what you do is you create your service abstraction, the protocol that defines what your service can do. And then you create your implementation. Let's say that we want to access our addresses model in the database using MySQL. And then when you go to register the service itself, instead of registering the MySQL address repository implementation, you register that underneath the protocol type itself. So when you access that within your application, you just use the protocol type, and then when you go to replace the implementation, you do it where you register the service itself, and then it works automatically everywhere else. Another feature that Vapor provides that I've noticed a lot of people miss out on is route collections. What you do is you conform your controller to the route collection protocol, and then you implement a boot method. And what this does is defines how your routes for that given controller should be registered to the application's router. And then what happens is you register the collection to your router instead of each individual route itself. And so this will define, and then that automatically registers the route handlers within your controller. And so it helps reduce the complexity in your routes function, because instead of individually defining how each route should be registered, it's just the collection itself. It helps organize your code and keep separation of concerns of how things should be work. So here's how a lot of people will define their controller. Let's say you have your database that you interact with, and then to get your to-do models, and then you have your routes themselves, your route handlers themselves. And then in your routes function, you create an instance of the controller, you create a routing group, and then you register each route handler underneath that group. And that works until you have 5, 10, 15, 100 different controllers that you're registering, and everything becomes a mess and hard to read. So instead, you conform your to-do controller to the route collection protocol, and you implement your boot method and here I'm creating the group like I did in the routes function itself, and then registering the handlers. And then when it comes time to register the controller to the routes, I can do a one-liner and just implement and register the controller that way. And it just handles the rest of it for me. Another thing that you can do that is less likely to be applicable but can still come in handy at times is putting your entire application in a provider. When you configure your Vapor application, what happens is you have your database config, and that's very specific to what database you're using. And then that kind of spreads into the rest of your configuration. It can get kind of messy and very specific to the database you're using. So what this does is it separates the configuration for the rest of your app from the database configuration itself. What you can do with this is skip the configuration in the application itself altogether and use it as a dependency instead. So you can import the provider into any project. And then, so if I have app A and make it a dependency to app B will automatically get all the features of app A. I can have custom boot sequences for each app instance. So once again, if I just create an application without a configuration, I can then create a bunch of apps that are only configuration, and then register the provider with those configs. And then the features of that app will work with the configurations that I use it with. Because you instantiate the provider before you register it with the services, you can pass values into that initializer and fine-tune how the provider should work if you happen to want to do that. And since you can extend services now in Vapor 4, you can register the services in the configuration themselves and then extend them in the provider registering method to customize it however you want. So as an example of what this might look like, you create your app provider. And in this case, I don't happen to want to fine-tune or anything, so I have an empty initializer. And then, as I explained earlier, I extend the default router, and I can register my controller with that. And then I register my migrations and my middleware, and then a counter service with whatever services are passed into there. And then my configuration gets really short. All I have to do is import the provider target and then register it with my services. So to recap about internal abstractions that are specific to Vapor and the repository pattern interfaces itself. Use interfaces to allow you to easily swap out the backends of data storage, whether that's through files or a third party, or whatever database you happen to be using. When you have a Vapor service, register it under the protocol type instead of its own implementation type, so that if you want to swap out what implementation you're using, you don't have to change the implementation itself throughout the entire code base, instead of waiting for your app to crash when you try to create a service that was never registered. Use route collections when you're creating controllers to just help keep your code organized and keep a separation of concerns. And if it's applicable to you, maybe you want to try putting your app in a provider. This isn't for everybody, but maybe it's a good case for you. And then check out the Vapor style guides. It's a really great document that covers more things about how you should structure your Vapor application and keep your code clean. And that's it. So right now I am open for taking questions. And if you want to get any links that you missed, they're up here, and there's another slide after that.